Okay, so in this section, we're going to be looking at non-homogeneous linear systems. And rather than come up with a brand new technique for solving these, we're going to use modifications of things we've already talked about. So we're going to be adapting the methods of undetermined coefficients and variation of parameters to solving these systems. In this video, we're going to look at undetermined coefficients, and in the next video, we're going to derive a method for variation of parameters to solve these guys. Now, just a quick disclaimer before we get started. These can be lengthy problems. If you remember from section 8.1, we showed that the general solution for a non-homogeneous linear system is going to take the form of a complementary solution plus a particular solution, just like in chapter 4 when we solved non-homogeneous equations. Section 8.2 showed us how to find this because, again, finding a complementary solution is the same thing as finding the general solution for the associated homogeneous equation. And that's all we were doing back in 8.2, finding solutions for homogeneous systems, not equations. So for that reason, I'm not going to spend the time that it takes to find this guy and do all the work. I'm simply going to give you the complementary solution for each example that we do, and instead focus our time on finding that particular solution, because that's the new thing for this section. So I give you that disclaimer because if you're kind of blowing through these videos and trying to learn just by reading the notes that I post, you're going to see me give the complementary solution with no work, and you're probably going to be scratching your head wondering where that came from. So again, our focus is on just finding the particular solution, and that's where the bulk of our work is going to go into. Second thing I want to say is that depending on the examples that we're doing, they can sometimes involve solving large systems of equations. And for example, this first example that we're going to work through is going to lead us to a system of 4 linear equations in 4 variables. And those are algebraic equations, not differential equations. It's a lengthy process solving those guys. And for that reason, I'm not going to go through all of the work that it takes to solve that system of equations. I'm going to kind of describe what we would do and then give an answer. And the reason for that, again, is not to devote so much time to just algebra. We want to focus on kind of the main new topics here. So with all that said, this is a non-homogeneous system. Notice it's of the form x prime plus ax plus f, where f is some vector having functions of t in it. And if we were to find our complementary solution for this guy, we would look for the eigenvalues of this matrix A. They turn out to be complex in this case. Specifically, we end up with a plus or minus 2i. And so what you would do is you'd go through the process that we talked about in 8.2 for that case 3, where we found general solutions for homogeneous systems where you had complex solutions. And our solution in this case, if we combine some things to keep it from getting too messy, is going to look like this. C1 times, where did I put it? Oh, there it is. Cosine of 2t plus 2 sine of 2t, and then cosine of 2t down here, plus c2 times negative 2 cosine of 2t, plus sine of 2t, then sine of 2t down here. Okay, so that's our complementary solution. Now what we need is a particular solution. And just like with undetermined coefficients back in chapter 4, the way that we go about finding a particular solution is we look at this guy right here and we use that to suggest what a solution might look like. When we've seen sines and cosines showing up, what we want to do is use a linear combination of sines and cosines in our particular solution. And we can write that this way. I can write a1, b1 times cosine of t plus a2, b2. Sorry, I wanted this one to be a sine of t. Sine of t plus a2, b2 cosine of t. Okay? So in order to use this in my linear system, I also need the derivative xp prime so I can plug it into this side. And that's going to look like this. A1, B1, cosine of t. Cosine of t has a derivative of negative sine. The negative I can bring over here and change that plus into a minus. A2, B2, sine of t. Okay, so now what I'm going to do is plug these guys in to the original equation up here. And I'm going to use that to equate coefficients to create this system of equations that I want to solve. So xp prime is going to show up on the left. Let's take that guy and put it on the left. A1, B1, cosine of t minus a2, b2, sine of t equals my coefficient matrix, -1, -1, 5, 1, times xp, which looks like this, plus sine of t, -2 cosine of t. Okay. Now, we have a property of matrix multiplication that you would learn in linear algebra, which says that matrix multiplication is distributive. So I can distribute this 2 by 2 matrix into each of these terms. And if you think about what that's going to do, is it's going to give me a new coefficient matrix on my sine of t and a new coefficient matrix on my cosine of t. And so what I want to do is find what those are equal to and then add this matrix to those results also. So let's think about that for a second. For my sine of t, I have to take this coefficient matrix a1, b1 and multiply it to this guy. So what's that going to look like? Well, on my sine of t, I'm going to have -a1 plus 5b1. -a1 plus 5b1. And then in addition to that, once I've done that, there's also this guy out here which has to be added to the result of all this. And because there's a sign present here, there's going to be a +1 that shows up because that's the coefficient on that sign right there. So +1. And this is going to be my sine of t. And then for the second entry down here, I'd be multiplying this column matrix to this second row here. That's -a1, so -a1 plus b1. And then my second entry down here doesn't have any signs in it. So I'm not going to be adding any additional constants down here. Now we do the same thing with the cosine. So I'm going to have a2 times -1, that's -a2. b2 times 5, that's plus 5b2. And then because it's in the first row that we're dealing with, I would also add this first row, but there's no cosines here, so there's nothing to add. Now we do the second row. a2 times -1 would be -a2. b2 times 1 is just plus b2. And then I also have this -2 cosine of t, so there's a coefficient of, or a constant of -2 that needs to be included there. Cosine of t. Okay, now if you notice I have a linear combination of sines and cosines here, where I'm kind of using the term linear combination loosely because these aren't constants, but they're matrices filled with constants. And because this is supposed to be an identity, I can basically just equate the matrix in front of the sine of t here to the matrix in front of the sine of t here, and then do the same thing with the cosines. And this is where I end up with a system of equations. So let's see what that system of equations would look like. Let's take this minus here. I'm going to distribute it up into my entries, so I'm being careful about what's being equated to what. And let's see what we have. I have a negative, well, let's start with here, the cosine. A1 should be equal to the top entry in my cosine matrix, so negative A2 plus 5B2. Okay, and then I'll equate the B1 to the second entry in this matrix. That's B1 equals negative A2 plus B2 minus 2. Okay, then I'll go to my sign here, negative A2, and set that equal to the first entry in this sign matrix here, so that's negative A1 plus 5B1 plus 1. And then finally, I'll equate this entry, negative B2, and that's going to be equated to this guy right here, negative A1 plus B1. Okay, so now, like I had said before, we have a system of 4 equations in 4 unknowns. And there's a couple of ways you could solve this. One way is to use a combination of elimination and substitution. And you can do that. You're gonna be juggling a lot of equations in that process. Another really good technique, if you've had linear algebra, you should be intimately familiar with this. Even if you haven't had linear algebra, you should have seen this at some point, but Gauss-Jordan elimination, which we talked a little bit about in the previous section. So I'm going to go that route, and I'm not going to do all the steps of Gauss-Jordan elimination. I'm going to set up an augmented matrix and then jump to an answer. So first of all, notice if I move all of my unknown terms to the left, I can rewrite this as A1 plus A2 minus 5B2 equals 0. And then I'm going to have A2 plus B1 minus B2 equals negative 2. Keep the constants on the right. A1 minus A2 minus 5B1 equals 1, and A1 minus B1 minus B2 equals 0. Okay, so what I'm going to do is create an augmented matrix. We talked about the notation for that in the previous section. My first column is going to represent the A1s, second is going to represent the A2s, third is going to represent the B1s, and my fourth column will represent the B2s. So looking at the coefficients on my A1s here, I have 1. There's no A1 showing up here, so that's 0, and then 1, 1. Looking for the coefficients on my A2s, I have a 1, 1, negative 1, 0. For my B1s, I have a 0, 1, B1 over here, negative 5, and negative 1. And then for my B2s, I have a negative 5. I have negative 1, 0, negative 1. And then my constants, I have 0, negative 2, 1, 0. 0, negative 2, 1, 0. Okay? To solve this, what you're doing is you're putting it in what's called a reduced row echelon form, which is just something that would look like this. Use row operations. Again, if you haven't used Gauss-Jordan elimination, you don't need to use this technique. You can use substitution and elimination. You'll get the same results. But we would use Gauss-Jordan to reduce this down to this guy. And what we're going to get is negative 1/3, positive 1/3, negative 3, negative 2/3. Okay? What these are the solutions for A1, A2, B1, and B2. And so that gets me my particular solution. Now I can write my final answer. So x is equal to my complementary solution, which we've written up above, And I'll just rewrite it here. C1 times cosine of 2t plus 2 sine of 2t cosine of 2t plus C2 negative 2 cosine of 2t plus sine of 2t. I got really cramped there. Sine of 2t, like that. And then I'm going to add my particular solution, which we just found the coefficients for. So remember, these two guys will be in the entry for my sine matrix, and these two guys will be in the entry for my cosine matrix. That's where they originally came from, up here. So this is going to look like plus negative 1/3 cosine of t plus negative 3, negative 2/3 sine of t. Okay? And that's going to be my final answer. So again, notice these are lengthy problems, and they're longer than we made it seem because, again, there's work that goes into finding your complementary solution. And then, when finding a particular solution, there would be work going into solving this system right here. Now, this one was particularly large as a 4x4 system, and a lot of the ones that you're going to see in the homework are not that large, but there's still a fair amount of work that goes into these. Let's do one more example. And this one's going to be a 3x3 system. This time, the f of t, the matrix that we're adding here to make this non-homogeneous, is a constant matrix. And these guys are nicer to work with. So let's, once again, get our complementary solution. And like we said before, we're not going to go through the work of finding that, but you would find the eigenvalues first. The eigenvalues in this case turn out to be plus or minus 5. And once you go through that, find the eigenvectors and whatnot, you end up with this as a complementary solution. C1, 0, 1, 0, e to the 5t plus C2, 1, 0, 1, e to the 5t plus C3, negative 1, 0, 1, e to the negative 5t. Okay? So like I said, we talked about how to find that back in 8.2, and we're not going through the time, not taking the time to develop that here. We want to just take a look at undetermined coefficients. So in this case, our suggested form for our particular solution is a lot more convenient than it was in the previous example, because we're just going to assume that we're dealing with constants. Say A1, B1, C1. In fact, let's just call it A, B, and C. I don't need the ones in there. A, B, and C. Okay? That means that xp prime is just the 0 matrix, the 3x1 0 matrix. So that's pretty nice. It's easy to work with. Okay? So now let's plug things in. xp prime is going to go here. So that's going to look like 0, 0, 0. Like that. Equals 5, 0, 0, 0, 5, 0, 0, 0, 5 times xp, which is A, B, C, plus 5, negative 10, 40. Okay? So if I do the multiplication here, notice A is the only thing when I do multiply this column matrix to this first row. It's the only entry that gets multiplied to a non-zero term. And that's going to give me A times 5, or just 5A. So that's going to look like 5A. Okay? Plus this 5 right here. Similarly, I'm going to get a 5b right there, 5b, minus that 10 right there. And then I'm also going to get 5c plus 40 right there. Okay? Oh, you know what? I'm realizing that there's a mistake made here. I think I had written these entries incorrectly. You know what? I'm going to go ahead and I am going to, yeah, okay, we need to make a little correction here. So I believe I typed this incorrectly. This matrix was supposed to have 5s. Actually, let me just double check my work here. I want to make sure I'm not correcting something for no reason. Yeah, so I meant to do this as my matrix. Yes, that's correct. So I had the 5s on the wrong diagonal. They should be going this direction. So I'm going to fix this real quick. This is still the correct complementary matrix for this guy, but I have some stuff that I need to fix here. So I'm still going to use xp equals ABC, which means xp prime is still equal to the 0 matrix. The only thing that's going to change is this step right here. So let's fix that. I'm going to have 0, 0, 0 equals 5, 5, 5. Make sure my 5s are in the right place there. Times A, B, C plus 5, negative 10, 40. Okay. So this should get us back on the right track. So what is this going to lead us to? Well, again, it's going to lead to a system of equations. I'm going to have 0 equals, when I multiply this column matrix to this row, it's going to be 5c plus 5. 5c plus 5. And then if I multiply this column matrix to this row, it's going to be 5b minus 10. And then same thing here. If I multiply this column to this row, 5a is going to equal, plus 0 equals 5a plus 40. Okay? Now this is a system of 3 equations and 3 unknowns, but each one of my equations only has one variable in it. So these are going to be really easy to solve. I just isolate the variable in each equation. Notice this gives me c equals negative 1, b equals 2, and a equals negative 8. So right away, I have my particular solution. That was a much easier one than the previous example. So now putting everything together, x is equal to my complementary solution, which we had up there. I'm going to write it again. C1, 0, 1, 0, e to the 5t plus c2, 1, 0, 1, e to the 5t plus c3, negative 1, 0, 1, e to the negative 5t, plus that constant matrix with a, b, and c in it. So that's going to look like this. Negative 8, 2, negative 1. Okay? That's going to be our final answer for this guy. Sorry about this. I didn't catch that when I was typing this, that I had the 5s on the wrong diagonal, but we fixed it, so we're good now. And that's all we're going to do for undetermined coefficients. Next up, we're going to look at variation of parameters.